Good morning, all of you. Welcome to Sri Jayendra Rank Zone. So far we have completed two lectures in chemical kinetics. Now I'm doing third lecture. So far we have completed order and molecular rate of the reaction, how to find rate of reaction, factors affecting rate of reaction, and now we are going to discuss new topic in this chapter. So this is very important chapter. Definitely you'll get one question for all competitive exams. Yes. So far we have completed how to find rate equation, order of reaction, and apart from that, order of reaction, molecular rate of the reaction in the previous class. Now we are going to discuss new topic in this chapter, very important. Please go through it. So, how to find integrated rate equations? Integrated rate equations. We have different types of order of reactions. For example, we have zero order reaction. What is a zero order reaction? Where the rate of the reaction is independent of concentration of the reactant. Zero order, first order, second order, and so on. Now we are going to discuss how to find integrated rate equations for these reactions. Let us see now. So first coming to, as noted earlier, the differential rate equation is expressed as rate is equal to K into A to the power of B, concentration of A to the power of B, concentration of B to the power of Q, concentration of C to the power of R. Now, however, it is not convenient to determine the instantaneous rate, that is dx by dt of a reaction, dx by dt of a reaction. So the problem can be overcome by integrating the differential rate equations to get a relation between the experimentally determined concentration at different times and the rate constant. Since we already know the order of reaction is nothing but it's an experimental quantity, it is not that based on stoichiometric chemical equation, whereas molecularity is not experimental quantity, it is based on stoichiometric chemical equations. So to find the instantaneous rate of a reaction, we need to differentiate them by integrating the differential rate equations. So that only we are going to do now. Just go through it clearly. So integrated rate equation for zero order reaction. Now the topic is, for zero order reaction, the rate of reaction is proportional to the concentration of the reactant raised to the power zero. Already we know that because it is independent of concentration of reactant. Always rate is proportional to concentration of reactant, but in this case it is power zero because it is independent of concentration of reactant. The rate of reaction is independent of concentration of reactant, so that's why it is called zero order reactions. Examples: photochemical equations and certain other examples already discussed in the previous class. So now, in other words, the rate is a constant. R is proportional to P. Where, so for example, take a reaction, reactant changes to product. Now, as the time increases, the concentration of reactant decreases. So that's why we use negative sign. That is differentiation of concentration of R by dt. There, where R is called concentration of reactant, which is equal to K into R to the power of zero. Here, zero is very important because it is a zero order reaction. So rate is equal to K into concentration of R, that is reactant whole to the power of zero. Since R to the power of zero is equal to 1, so by this we can say differential rate equation differentiation of concentration of R is equal to minus K dt coming this side. So integrating the rate equation. So by integrating, we'll get differently. So that integrated rate equation is important. So R is equal to minus Kt plus C, where C is called the constant of integration. Let R naught and R naught means initial concentration, and R be the final concentration at the time T of the reactant. At T is equal to 0, R is equal to R naught, because concentration of R becomes R naught because at T is equal to 0. Since initial reactant is concentration of reactant is R naught, and equation 1 becomes R naught is equal, that is T is equal to minus K into 0 plus I R C, that is equal to rate constant. Hence equation R becomes R minus R naught is equal to KT. R minus concentration of R minus concentration of R naught is equal to KT. This is the integration formula. R K is equal to initial concentration and concentration after time t seconds by t. K is equal to x by t, where x is the amount of reactant reacted. X is the amount of reactant reacted. Very important. So this is the formula for finding integrated rate equation for zero order reaction. So this is the formula. You have to remember this formula. This is the application formula. How to find rate constant for zero order reaction? Rate constant K is equal to initial concentration of the reactant minus concentration of the reactant after time t seconds divided by time in seconds or minutes or hours depending on the numerical. So our K is equal to x by t, where x is the amount of substance reacted. Amount of substance reacted is also the same thing. R naught minus R is called x. R naught minus R is equal to x. So R is equal to minus kt plus R naught. The equation is in the form of y is equal to mx plus c, representing a straight line. So a plot of R against t will be a straight line with the slope minus k and intercept. This slope is equal to minus k and intercept is equal to r naught. That's what I have given already the graph like this. So if you take the concentration of the reactant and with respect to time, for zero order reaction, it is a straight line parallel to x-axis. So straight line because there is no effect on the concentration of the reactant with respect to time. So that's why minus k, the slope is equal to, for this the slope is equal to slope, for this graph the slope is equal to minus k, and intercept is r naught. Intercept is how much? R naught. Intercept is equal to r naught. I hope it is clear. So this is very, very important formula. Please note down this formula. I'm clearing all the drawings. Now let us continue with them. So this is the slope and it's a decreasing. Actually, if you take the slope like this, you will get the graph like this. But normal graph, if you want to represent, as I previously I have given the same thing. The concentration of reactant decreases with respect to time, but it is not with respect to time because it is a zero order reaction. I hope it is clear. Next, for first order reaction. Now integrated rate equation for first order reaction. For zero order reaction, K is equal to x by t. Now we are going to discuss how to find integrated rate equation for first order kinetics. So first order reaction, already you know, R changes to product. The rate is proportional to the first power of the concentration of the reactant. So since rate is equal to minus dr by dt, that is equal to K into concentration of R to the power 1. So one is not equal to one is not required to mention because it is R given. So that's why I written R. So and dr by dt is equal to minus k dt. Integrating the rate equation. So by integrating we will get clearing the drawings. So INR, that is natural logarithm, is equal to ln R is equal to minus kt plus c, where c is the constant of integration. At t is equal to 0, R is equal to R naught, and the equation becomes ln R naught, that is minus k into 0 plus c. So all these things no need to see, simply directly just listen carefully. Minus k into 0, this is the derivation which is given in the textbook, also NCERT textbook. So step by step you try to understand. So ln R, that is concentration of reactant, minus Kt plus C, where C is called the constant of integration, and at T is equal to 0, minus K into 0 plus C is equal to, or C is equal to IN, Ln concentration R naught. Hence equation 1 becomes Ln concentration R, Ln is called natural logarithm, minus Kt plus Ln concentration of R naught. By this we can write R naught, we have sent this side, so Ln R naught minus in ln r is equal to kt. By this you can say k is equal to 1 by t ln r naught by r, which also can be taken as k is equal to, since for removing natural logarithm we have to use the multiplication 2.303. So k is equal to 2.303 by t into log base 10, log base 10 concentration of r naught by r. This is the application formula for finding for finding first order kinetics rate equation. So K is equal to, what is the formula? K is equal to 2.303. K is called rate constant. It is measured in second inverse. So K is equal to 2.303 by T. T is called time, and log of R naught, initial concentration by final concentration. R is equal to concentration R, where T is equal to R is equal to uh, final concentration, or the amount of substance reacted. So I hope it is clear. Next. So equation 3 may also be written in the exponential form. So that is ln r naught is equal to minus kt or e power minus kt and so on. However, we'll use this formula only. K is equal to 2.303 by t into log base 10 AMI by A minus x, where A is called initial concentration, initial number of moles, and x is the number of moles reacted. that is A minus X. Very, very important. This formula only application formula. So I hope it is clear. Next, graphical determination of K. Equation 4 may be regarded as log of R naught minus R. So you will get a graph y is equal to mx plus c. This slope is important. So this is a graph of first order kinetics, log concentration of R to the respect to time. So these graphs are very important. They'll ask graphs in the examination. So which of the following graph represents first order kinetics? Which of the following graph represents zero order kinetics? So for first order kinetics, log R concentration of R, log R naught, slope is equal to minus k by 2.303, and time. So this is the graph, very, very important graph. So the graph representing first order kinetics is this. Zero order kinetics already we have seen. First order kinetics. These graphs they'll ask in the examination also, and this is the application formula. I hope it is clear. So how to find rate equation for first order kinetics? So by this, we can say graph of log R to t will be a straight line with intercept log R naught minus slope is equal to minus k point 2.30. This slope value is also very important. They'll ask what is the slope of first order kinetics, what is the slope of zero order kinetics. So ln R, concentration R gives us to t is plotted intercept, and this is slope is equal to minus k. So equation 4 can be regarded as log of concentration of R naught by R is equal to KT by 2.303. This is in the form of Y is equal to mx plus C. So by this we can say passing to the origin slope is equal to K by 2.303. This slope is very, very important. They'll ask slope only from this. So application formula also important, slope is also important. So continuation, this is the graph. Log R naught by R, if you take, you'll get a straight and parallel like this increasing line. If you take graph for log R naught by R, this is also very, very important graph. So this is a graph presenting. And what is the equation for finding K is equal to 2.303 by T into log of A by A minus X. This is called the differential rate equation for first order kinetics. Differential rate equation for first order kinetics, where A is called initial concentration or number of moles, and A minus X is called number of moles reacted, and X is called number of moles reacted, A minus X is number of moles left. So this is the very, very important rate equation. So after get formula. So relation between rate constant and concentration of reactant at two time intervals, very, very important. For first order kinetics at time t1, ln R1, concentration of R1 is equal to minus KT1 ln R0. This is the integrated rate equation. At time t2, the same thing, minus KT2. K remains the same because it is called rate constant. Here, concentration of R1 and concentration of R2 are the concentration of the reactant at time T1 and T2 intervals. Next. So subtracting 2 from 1, we got K is equal to 1 by T2 minus T1 ln R1 by R2. The same formula you can represent in the examination point of view. If they are given two intervals, two time intervals and two rate initial concentrations, then we can how to find K is equal to 1 by T2 minus T1. For removing natural logarithm ln, we have to use 2.303 log of concentration of R1 by concentration of R2. I hope this is the formula. This formula you have to apply in the examination. Okay. Now it is clear. So only formulas are important. They will not ask anything in the examination point of view, objective point of view. They will not ask derivation. So formula remembering is very important. Now we'll see example one. While studying the decomposition of gases N2O5, it is observed that a plot of logarithm of its partial pressure versus time is linear. Linear. What is the order of reaction? Linear means it is, you know what is linear means, it is a straight line inclined to the time axis. So it is first order reaction. Since the graph is linear, we can say it is first order reaction. I hope it is clear. Next, for a zero order reaction, K is equal to 1 in 10 to the power minus 3 moles per liter per second. If initial concentration of the reactant is 1 moles per liter, then the concentration after 10 minutes would be very, very important. So K is equal to, for zero order reaction, K is equal to X by T. So substituting that formula. So for zero order reaction, K is equal to X by T. This is the rate equation for zero order chemical kinetics, integrated rate equation. So K is equal to X by T. T is equal to 10 minutes. X is given as, K is given as the concentration after 10 minutes. They are asking us X how to find. So K into 10 minutes. That's nothing but x is equal to kt. So x is equal to kt means initial concentration is given. So x is equal to k into t. K is equal to 10 into 10 to the power of minus 3. Sorry, 1 into 10 to the power of minus 3. So k is equal to 1 in 10 to the power minus 3 and t is equal to 10 minutes. And after substituting this, you will get the formula. And here it is given 1 moles per liter. 1 minus x we have to take. 1 minus x. So this should be taken as 1 minus x because initial is 1. So answer will be for this is equal to, for this the answer will be 0.6 mole. How we got 0.6 mole? So x is equal to k by t, k into t, k is equal to x by t. You can just see, I'm just recapping it now. Just please go through it now. Here again I'll show the formula for zero order kinetics. I'm showing the formula so that you can understand easily. For zero order kinetics, you can see here the formula. K is equal to r naught minus r by t. K is equal to what? So here I'm showing it here. You can see k is equal to r naught minus r by t using the same formula we are going to do now. You can just see here. Second example we are going to now. So k is equal to r naught concentration of r naught minus concentration of r by t. So simply you can use this formula. So k is given already 1 into 10 to the power of minus 3. 1 into 10 to the power of minus 3 into time is 10 minutes is equal to concentration of r is initial 1 minus x. So x is equal to how much? That only you have to find. So I hope it is clear. Easily you can understand, and it is answer is equal to 0.6 moles. 0.6 moles per liter. Next question. The specific rate reaction for a first order reaction is 0. Reaction rate for a first order kinetics is 0.02 second inverse. So what is this called? This is the value of k. The value of k. And the initial concentration of the reactant is 2 moles per liter. So A is equal to 2 moles per liter. Calculate the initial rate and rate after 60 seconds. So how to find the initial rate and rate after 60 seconds? So K is equal to, for first order kinetics, R is equal to K into concentration of R. So K is given, R value they are asking. So K by, so R is equal to K into K is given 0.02 into 2 because initial concentration is given 2 moles per liter. So 0.02 into 2 is 0.04. 0.04. So this is the value of R, that is called initial rate, and rate after 60 seconds. So since K is equal to 2.303 by T into log of A by A minus X. So initial rate we know, so A minus X. So by using this formula, you can find the rate after 60 seconds. So rate after 60 seconds means K value will never change. So K into R minus R naught by T, or you can say K into R minus R naught by T is equal to R. Even no need to use this formula also. One more small easy formula I'll tell you. They are asking rate, they are not asking rate constant. So rate after time t seconds is equal to R is equal to K into R minus R naught. That is initial minus final. So R naught minus R because it is decreasing. So if you multiply this, you will get the answer. So R naught minus R. Since you know the rate, by this you can say, so for example, R is 0.04 is equal to, so rate only we have to find, no need to take R value 0.04. So use this formula or that formula, so you get the answer clearly by T. Because after 60 seconds. So I hope it is clear. So first formula, first one is 0.04. Next one you will get some value after substituting that formula. So please check these answers. So first is 0.04 moles per liter. This already we have got. And next will be 0.012 moles per liter per second. That is the rate after 60 seconds. Rate after 60 seconds. This is very, very important. So I know how to find it. So I hope you understood how to find these questions. Next, example for first order reaction, A gives rise to B plus C. The concentration of A was found to be 0.6 molarity. Initial concentration is 0.6 molarity at the 10th minute and 0.5 molarity at the 20th minute after the start of the reaction. Calculate the rate constant of the reaction. So they're asking us to find rate constant. So K is equal to 2.303 by T into log of A by A minus X. So let us take initial concentration is equal to 1 molarity because after 10th minute it changes to 0.6 molarity. So you take A is equal to 1 molarity initial concentration, A minus X is equal to 1 minus 0.6, that is equal to 0.4. So substituting these values and T is equal to any one interval you take because they're asking only a rate constant. So you need to take two intervals, only one interval, that is 10 minute, 10th minute. So if you take 10th minute, so what is the time? Time is equal to 10 minutes. So substituting T, A minus X, and you can find out K because they're asking rate constant for the reaction. I hope it is clear. So 1 by 0.4 into 2.303 by 10 into log of 1 by 0.4, log A by log B, log A minus B, log A minus B. So if you do calculation, you'll get the answer, and the answer is 0.018 minute inverse. This you can understand clearly. Even you can do the formula based, even you can do like this also. One more formula is also there. Same question, one more formula. K is equal to 1 by T2 minus T1 into 2.303 the log of initial concentration by final concentration. Even these formulas you can do, so that you can apply this formula. 1 by T2 minus T1, 10, 20 minus 10, that is equal to 10 into 2.303. As I told you, the same formula you'll get into log base 10. Concentration of R naught initial is 0.6 by 0.5. So 0.6 divided by 0.5, if you do calculation, you'll get the answer is equal to 0.018. I hope this is clear. So this is the steps involving for finding. You can use this formula or you can use rate constant. Just I have given one, only taking one interval 1 minus 0.6, that also you can do. This also there is it. There are two ways to solve this problem. This is the second way, and first way I already have given you. The first way is what? K is equal to 2.303 by 10. Only first interval I am taking into log of A. A is initial molarity. It is 1 molarity. Let us example 1 minus 0.6. So the same thing you'll get here also for this and for this also you'll get the same values. I hope it is clear. You can check the answer by applying any of the formula. So next. So we have successfully calculated how to find rate equation, integrated rate equation for zero order kinetics and also first order kinetics. Let us see the next topic in this chapter. Yes, I'm starting it now. Yes, it's coming now. The next topic in this chapter we are going to do now. So only first order kinetics problems only important for examination point of view because NCERT based questions also we have only first order kinetics questions. And experimental determination of the rate constant of acid hydrolysis of an ester. Rate constant of acid hydrolysis of an ester. Let us see now. So you know ester on hydrolysis forms acid plus alcohol. The reaction started by mixing and this is called pseudo unimolecular reaction. These reactions are called what? Pseudo unimolecular reactions where the molecularity is 2, pseudo unimolecular, and the order is 1. How for this reaction order is 1, that we are going to demonstrate now. Pseudo unimolecular reactions. So hydrolysis of esters gives acid plus alcohol. The reaction started by mixing an ester like ethyl acetate with a standard solution of HCl, say 0.5 molarity, and acid hydrolysis. So in presence of acid, The progress of the reaction is monitored by withdrawing definite volumes of the reaction mixture, say 5 ml from time to time, and titrating it with NaOH solution. So the titrate value is noted at the start of the reaction, where initial volume is V naught and a definite time intervals Vt, and after the completion of the reaction V infinity. So we have three different volumes. What are those? Initial volume V naught, after in between the time T Vt, and after the completion of the reaction V alpha. So by using these calculations, we are going to derive now the formula. So V naught is proportional to amount of HCl present as catalyst. This is constant. Vt is proportional to amount of HCl plus amount of acetic acid formed at time t seconds, and it is observed. These are all experimental data. So Vt is proportional to amount of HCl plus amount of ester reacted also, and V infinity is proportional to amount of HCl plus amount of acetic acid formed after completion of the reaction. So V infinity is proportional to amount of HCl plus amount of ester present initially A. So by this, we can say simple direct formula. You know the integrated equation for first order kinetics. K is equal to 2.303 by T log of A by A minus X. Since A is equal to number of moles and it is volume. So volume will be inversely proportional to number of moles. So K is equal to 2.303 by T log of V infinity minus V naught by V infinity minus Vt. This is the formula for finding volume. Volume in case of volume, if they ask us to find volume, and how to find rate constant for the reaction, you have to use this formula. So when they have given volumes and you need to find rate constant, use this formula, that is K is equal to 2.303 by time into log of V infinity. V infinity means final volume minus initial volume by final volume minus volume after t time t seconds. So this is very, very important formula. So if they have given, instead of giving number of moles, if they have given volume, you have to use this formula. I hope it is clear. So please note down this formula whenever you get numerical like this. Anyway, we are going to do all the types of numericals in the end. So just now we are discussing all the topics. After finishing the concept, we'll do the numericals with the immediate effect. So I hope it is clear. Next example one. Now you can see here 1 ml of methyl acetate, this is ester, was added to 20 ml of 0.5 normal HCl, and 2 ml of the mixture was withdrawn from the time during the progress of hydrolysis of ester and titrated with a solution of alkali. The amount of alkali needed for titration at various intervals is given below. Time initial 0 minutes, alkali used in ml 0, it is given. So establish the reaction is that of first order. We have to show it is first order kinetics. So infinity 26.6, 42.3. So it is a first order reaction because how it is proved, because you can take the time interval. So we can take like this. So K is equal to 2.303 by T into log of V infinity minus V naught by V infinity minus Vt. Use this formula and you will notice that it is based on first order kinetics. If you observe two intervals, it will be increasing with the time, with respect to time. So for 0, it is 0. So after 20, 19.24, after 119, 20.73, and at infinity 26.6, they have not given the problem numerical properly. So whenever they have given first order kinetics with respect to time, it is keeping on increasing. The concentration of reactant decreases with respect to time. The concentration of reactant decreases gradually with respect to time. Very, very important. So this we have to go through it. Next, rate constant of first order reaction in terms of initial pressure and total pressure. So what happens when they are given? If they are given volumes, you have to use this formula. And if they are given number of moles, you have to use K is equal to 2.303 by T into log of A by A minus X. Whereas now next is, if they are given pressures, pressure also will have concentration. So this method is generally used for gaseous reactions involving the decomposition of a substance, like decomposition of nitrogen pentoxide, dinitrogen pentoxide. So the initial pressure Pi of the reactant is first measured. The total pressure of the reaction mixture at different time intervals Pt is also measured. From this data, K can be calculated. What is K? Rate constant. Consider the first order gas phase reaction as a decomposition of 1 mole of A to give 1 mole each of B and C. 1 mole each of B and C means the reaction is what? A gives rise to B plus C. What is the reaction? A gives rise to B plus C. So for this reaction, Let x be x atmosphere be the decrease in the pressure of A at time taken. Anyway, when that after passing of time, what happens? The pressure in A decreases and goes to pressure B, and pressure C will increase. So the increase in pressure of B and C will also be equal to x atmosphere each. So initially it is 1, it is 0, this is 0, this becomes 1 minus x, and this becomes x, and this becomes x. So in this way you have to calculate decomposition. So I hope it is clear. Now we'll see how to calculate when the pressures are given. Just formula will change that. So see, as I told you, at T is equal to 0, P initial atmosphere is Pi, and initially there is no formation of product. That's why you have written 0 and 0. After time, at time T seconds, what happens? The initial pressure decreases, that is P minus X. How many times it decreases? X times. So P minus X ATM, and this is X atmospheres, and this is formation of X atmosphere. So total pressure is equal to total pressure PT is equal to partial pressure of A plus partial pressure of B plus partial pressure of C. What is partial pressure of A? It is equal to applying Dalton's law. Total pressure is equal to P1 plus P2 plus P3. So Pi minus X plus X plus X. So that becomes minus X plus X gets cancelled. So it becomes Pi plus X. So our X is equal to Pt minus Pi. Very, very important. So X is equal to the decrease in the pressure is equal to total pressure minus initial pressure. The decrease in pressure is equal to total pressure minus initial pressure after t time seconds. So Pa is equal to Pi minus x, this already we know, and Pi minus Pt minus Pi, that is x value we are substituting here. So that becomes 2 Pi minus Pt. So partial pressure of A becomes 2 Pi minus Pt. So substituting this value, K is equal to 2.303 by T into log of Pi by 2 Pi minus Pt. 2 Pi minus Pt because it is equal to 2 times of pressure Pi minus, where Pi is called initial pressure minus Pt is called final pressure after t times 60 seconds. So this is the formula we are going to use, log base 10. So this is the application formula. So let us see the numerical on this. So this formula, please remember all of you, this formula. How we got 2 Pi minus Pt, I hope it clear. So pressure of A is equal to Pi minus x, already we know, which is also equal to, since x is equal to Pt minus Pi, that is total pressure minus initial pressure. So Pi minus Pt minus Pi, taking 2 Pi common, 2 Pi minus Pt. That is 2 times of initial pressure minus Pt. That is pressure of after time t seconds. So you can ask this, they'll ask questions on this. Now example, this example is same thing. For a gaseous first order reaction of type A gives us 2B plus C, very, very important, 2B they have given. Starting from pure A with an initial pressure of, so Pi is given, how much it is given. So I'm writing here itself what is Pi. Pi is equal to initial pressure is equal to 500 atmosphere, 500 millimeters of Hg. The total pressure of the reacting system after 20 minutes is 700. Total pressure is also given, Pt is also given, and calculate the rate constant. Let us write the equation first. A gives rise to 2B plus C. There it is just only. So initial pressure is Pi, and this becomes 0, this becomes 0. Now final pressure after time t seconds, that is Pi minus x, Pi minus x, and this becomes 2x, and here it is x because this is 2 moles. So Pi minus x plus, so the total pressure is equal to Pi minus x plus 2x plus x. So this becomes Pi plus 2x. So this becomes total pressure is equal to Pi minus 2x. So Pi plus 2x, total pressure is equal to Pi plus 2x, initial pressure. So by this you can find out total pressure is equal to Pi plus 2x. By this you can write x is equal to 2x is equal to P minus Pi. That is total pressure, P total actually. Sorry, here you have to write P total. So P total. So 2x is equal to Pt minus Pi. So x is equal to Pt minus Pi by 2. Pt minus Pi by 2. So substituting these values in the equation, you'll get the answer. So x is equal to what? Pt minus Pi by 2. They're asking calculate the rate constant. So first we have to find x value. So x is equal to how much? It is equal to Pt minus Pi by 2. So Pt minus Pi by 2 is equal to x. So for this, the integrated equation becomes, so finally you can find x also, because 700, this total pressure is 700 minus initial pressure is 500 by 2, which is equal to 700 minus 500 by 2, that is 200 by 2. 200 by 2 is equal to 100 atmospheres, 100 mm. So this is pressure decrease. So 500 minus 100. So this becomes, now K, how to find K is equal to 2.303 by time. Time is given 20 minutes into log of Pi minus final pressure. It becomes Pi plus 2x. That is x is equal to Pt minus Pi. Pt minus Pi by 2 minus Pi minus Pt. So this is 100 minus 600. So if you find the log values and taking this formula, you'll get the answer. I hope it is clear. So very important. Again, I'm explaining this problem. They have given the reaction like this. And for this reaction, initial pressure is Pi. And initial, there is no pressure of B and C. So it is equal to 0 and 0. Now total pressure after time interval, after 20 minutes, it is decreased. So 500 mm. The total pressure of the reacting system is given. So Pi minus x is equal to x into x. How much it is decreased? 100 times. So 500 minus 100, it becomes 400. So this becomes 400 plus 2 into 100, 200 plus 100, 300. So totally you'll get like this. And after finishing this, you'll get the answer. And after substituting, you can use the formula. I'll show you the previous formula during all the drawings. Just so you have to use like this. So answer, final answer you'll get the rate constant is equal to 0.0115. So straight away how to apply rate constant formula I'm writing here. K is equal to 2.303 by T into log of Pi, that is initial pressure, by Pt minus Pi. Sorry, 2 times of Pi, no? Yes, 1 minute, just wait. So this 2 times of Pi minus Pt. So this is the formula for finding, where Pi is called initial pressure 500, Pt is called total pressure 700. Pt is equal to Pi is equal to 500 mm. Pt is equal to 700 mm. So by substituting this formula, 100% you'll get K value, and K value will be minute inverse, and T value is equal to 20 minutes. 20 minutes. T is equal to 20 minutes. Since the answer is also given in minutes, so no need to convert minutes to seconds. So it's 20 minutes. So I hope it is clear. You can do the numerical like this. Next question. The decomposition of Cl2O7 at 400 kelvins in gas phase to give Cl2 and O2 is a first order reaction. They have given this equation is Cl2O7 changes to Cl2 plus O2. So Cl2O7 changes to Cl2 plus O2. Now to find anything here, because stoichiometry equation only take, but because they are asking rate constant. The presence of Cl2O7 falls from 0.062 atmosphere to 0.044 atmosphere in 60 seconds. So they are given final pressure, initial pressure. They are asking rate constant. Same formula. Apply this formula. What is the formula here? Rate constant they are asking. So K is equal to 2.303 by T, that is 60 seconds, because T value is 60 seconds, into log of P initial by P initial minus P final, that is P total. This falls from P final actually. It is not P initial minus P final. So this formula, if you substitute the formula, because they are not given total pressure, so straight away you can use, because if they are asking this is a first order reaction, so use this formula, integrated rate equation. K is equal to 2.303 by T log of Pi. Pi is called what? Initial pressure 0.062 and final pressure becomes 0.044. 0.044 and time is given 60 seconds. So use this formula. Pi by Pi minus Pf. Pf is called final pressure after time 60 seconds. So I hope it is clear. Use this formula, 100% you'll get the answer. Let us see the answer. It is 0.171 second inverse. You can check the answer after substituting the values. Next. The decomposition of nitrogen oxide at 900 kelvins follow first order kinetics. Nitrogen oxide. So the initial pressure is 200 mm. The pressure actually, this is wrong given here. The pressure drops. Pressure falls actually. Pressure drops. Both are same. 120 millimeters in 30 minutes. From 200 it came to 120 millimeters in 30 minutes. Calculate the weight constant partial pressure of N2O at 50 minutes. So to find partial pressure is equal to partial pressure P naught is equal to total pressure into mole fraction. Total pressure into mole fraction. First we can find out K. Rate constant K is equal to same formula 2.303 by T, that is 50 minutes into log of 30 minutes into log of concentration of A, concentration of P, that is P naught P initial by P initial minus P final, that is PT. So it is not PF, it should be PF. So 200 changes to 120. So 200 minus 120, 200 by 200, that is equal to 2.303 divided by T value is given 30 minutes in the first case, 30 into log of PI. Initial pressure is 200 mm by 200 minus 120. Simple formula. We have to apply the weight equation the same for all. So definitely you'll get the value of K after finding K. So total pressure is, they are asking partial pressure of N2O, that is the nitrous oxide at 50 minutes. So partial pressure of N2O after 50 minutes means take T is equal to 50 minutes and find out the value of total pressure. Means after this pressure they are asking for 50 minutes. 50 minutes T is equal to 2.03 by K. So 2.50 minutes means after 50 minutes 50 is equal to 2.303 by K into log of initial pressure by Pi minus Pt. So from this you have to find this. I hope it is clear. So by seeing that answers you'll get the answer. So verify with the answer. It is 85.4 mm of 85.4. They have not given K value also, but anyway you'll get K value by substituting the same formula. And finally it becomes after 50 minutes still it is decreasing, it changes to 85.5, 85.4 mm. I hope it is clear. Next. So next we have very important concept in this chapter, that is how to find half-life of first order kinetics. So integrated rate equation for zero order with respect to what we have done so far, integrated rate equation for zero order reaction, integrated rate equation for first order kinetics, as well as also we have found how to find with respect to volume, with respect to pressure, with respect to number of moles. So all are most important. Let us see now half-life of a reaction. What is half-life? The time taken for the reaction to complete 50%. Simple. The time taken by the reaction to complete 50% is called half-life of a reaction. And in this case, the time taken by the reaction. See, the half-life of a reaction is the time in which the concentration of the reactant is reduced to one half. So concentration of the reactant only, because we are considering only reactants, to one half of its initial concentration. So let us say initial concentration 1 molarity. The time taken to become the concentration of the reactant to 0.5 molarity is called its half-life. So the half-life of a reaction is the time in which the concentration of a reactant is reduced to one half of its initial concentration. So the half-life period is different for reactions with different order. For T half zero, for zero order reaction, this is very important. For zero order reaction, T half is equal to K is equal to R naught R minus R by T, where at half life T is equal to T half. So R is equal to R naught by 2. So R naught minus R naught by 2 by T half. So straight away we'll get the formula T half is equal to R naught by 2K. For zero order, you have to use this formula for finding half-life of zero order reaction. Initial concentration by 2 into 8 constant. 2 into 8 constant with respect to zero order reaction. So this is called. And first order reaction, R naught by R, if you take into consideration, just we are deriving it. So T half is equal to, for first order reaction, first order reaction, since T half R is equal to R naught by 2, because initial concentration by 2. So K is equal to 2.303 by T half into log of R naught by 2. So by calculating this, you will got finally 0.693 by K. So this is the application formula. So half-life of first order is 0.693 by k, whereas half-life of zero order is T half is equal to initial concentration by 2k. That is for zero order. This is T half for zero order reaction. Zero order reaction. So zero order reaction T half is this formula, and first order kinetics, first order reaction directly T half is equal to 0.693 by K. I hope it is clear. So half-life of first order reaction is constant and independent of initial concentration. Very, very important. They'll ask half-lives also to find. So T half is proportional to R naught and T half is proportional to A to the power of n minus 1, where n is the order of the reaction and R naught is equal to initial concentration of the reactant being the same for all reactants. So for zero order, T half is equal to this table is very, very important. 100% you'll get question from this table. So what is this table? For zero order reaction, T half is equal to A by 2K, where A is called initial concentration of the reactant. For first order kinetics, 0.693 by K. And for second orders, 1 by K R naught into K naught. And for any order of the reaction, this is the actual reaction. That is T half is proportional to 1 by concentration of R naught whole to the power of n minus 1, or T half is proportional to 1 by concentration A to the power of n minus 1, where n is the order of the reaction. So for zero order, 0 minus 1. For second order, first order, third order. So this table is, this page is very, very important. These formulas they'll ask in examination to calculate. So for zero order reactions, T half is equal to A by 2K. For first order reactions, T half is equal to 0.693 by K. For second order reaction, T half is equal to 1 by Ka. 1 by K into A, where A is called initial concentration of the reactant. K is called rate constant of that second order reaction. K is called rate constant of first order reaction. And K is called rate constant of zero order reaction. So that is change. So I hope it is clear. So these formulas are very, very important. Very, very important. Please note down. So the half-life of a reaction is determined for two different initial concentration of the reactants. The order of the reaction is calculated by using the relation T half 1 by T half 2. So if you are using the two different reactions half-life, so you can use T half 1 of first reaction by T half of the second reaction is equal to A2 by A1 whole to the power of n minus 1, where A2 is called initial concentration of second reaction, A1 is called initial concentration of the first reaction whole to the power of n minus 1, where n is called order of the reaction. I hope it is clear. This formula is also important. The half-life of the reaction is determined for two different initial concentration of the reactant. The, the order of the reaction is calculated by using the relation. Now, the half-life of first order reaction is 50 minutes. Calculate the rate constant time required to complete 75% of the reaction. Very, very simple question. They're asking half-life T half of first order reaction is 50 minutes. So T half is equal to, T half is equal to 0.693 by K. Implies K is equal to, because that is called rate constant, K is equal to 0.693, 0.693 by T half. So T half is given 50 minutes. You have to change them into seconds. So K is equal to 0.693 divided by T half value is given 50 minutes, 50 into 60. And now you'll get the answer. If the answer is given in minute inverse, you'll get no need to join 60. If they have given second inverse, you have to take the concentration. So 0.693 divided by 50, that is 0.01386. You'll get, if the answer is given in minute inverse, you'll get. So you have to find K value for this. Now after getting K, so how to find time taken for the reaction to complete 75% of the reaction. So to complete 75% of the reaction, we can use this formula. T is equal to first order kinetics 2.303 by K into log of 100 by 100 minus 75, because initial is taken as 100 and 75% is completed. So second instance you have to take like this, and whatever value of K here you got, you substitute the value of K here. So this is a two-step sum. First step, what you have to do, from T half you can find K directly by multiplying it by K is equal to 0.693 by T half, that is 50 minutes. So 0.693 by T, that is 50 into 60, you get K value. Substituting the value of K in this equation, you will get time taken for the reaction to complete 75% is equal to T 75% is equal to 2.303 by K log of 100 by 100 minus 75. I hope it is clear. So in this way, you have to calculate the sum. So answer will be for K value first. K is equal to 0.0181386 as I told you. They have given in minute inverse. So straight away use this formula since they have given minute inverse. So since K is equal to 0.693 by 50, which is coming around 0.01386. Now after substituting this, so T 75% is equal to time taken for the reaction to complete 75% is equal to applying integrated rate equation of first order kinetics, that is K is equal to 2.303 by T. So T sending this side, T is equal to 2.303 by K into log of A is 100, 100 minus 75, that is equal to 4, that is 1 by 4. Sorry, 100 by 25, that is equal to 1 by 4. So substituting the value of K in this equation, you will get T75 is equal to approximately 100 minutes. So definitely you will get the sum like this. So please do it like this. Next, I'll tell you the shortcuts also for finding that in the whenever time comes. The following data were obtained at a certain temperature for the decomposition of ammonia in contact with tungsten. So they have given tungsten different temperature. The following data are obtained at certain temperature for the decomposition of ammonia in contact with tungsten. So P 50 minutes, T half related to T half 3.64, 100 minutes 1.82, 200 0.91. Just it is decreasing exactly half, half, half. So order of reaction. So this order of reaction representing what? So for first order reaction we have T half is equal to 0.693 by K. For second order, we have to take into consideration for first order 0 order and for second order. So let us see now. For second order, how to find K value. So for first, I'll write here different orders. Yes. For 0 order, A is equal to 2 by K. T half is equal to A by 2K. For T half is equal to 1 by K into A, where K is equal to rate constant, A is called initial concentration. So let us check which is matching for this. You have to match for this answer only, that's all. So it will be easy now to understand. This we have to complete it next to this question only. So for 0 order, I'll write here, for 0 order, if suppose the reaction is 0 order, what is the reaction? T half is equal to A by 2K. And for first order, T half is equal to 0.693 by K. It's for first order. And for second order also you have to check. So this is matching with second order because it is decreasing two times, 3.64, and T half for 100 means it is nothing but 1.82. So exactly 2 times, 1.82 against 0.91. So this is nothing but it is in the form of A by 2K. So that is second order reaction. That is what reaction? Second order reaction. You can just, I'll show it clearly now. So this is of second order reaction because it matches with second order 3.64, exactly half is 1.82, exact 2 times decreasing is 0.8. 1.8 into 2 is 3.64. 0.91 into 2 is 1.82. So it is 2 times exactly. So it is second order reaction. I hope it is clear. Next question. So in this chapter we have done up to how to find rate equations and also how to find rate equation and how to find second order reaction, etc., etc. So very important this class. In the next class we'll do the other topic. I hope this is clear. So, and in the next class I'll tell you the shortcuts regarding how to find numericals in first order kinetics, only for first order kinetics. How to find half life also we have given. So I'm discussing now. So I'm going to stop sharing now. I hope it is clear. So all of you please understand and do numericals based on first order kinetics maximum, because the based on NCRT syllabus we have questions based on NCRT. We have only first order kinetics. So thank you all.